Another nice special case of finding a matrix for a linear transformation relative to some bases is if you really don't have a linear transformation and you just want to switch from one basis to another. So you want to say you have coordinates relative to one basis and you want to find coordinates relative to another basis. Right? So in this case, be a little careful. In this example, the v's and the w's are actually both bases for the subspace V. So there is no other subspace W, just V. So in this case, right, we have, so the coordinate map relative to our first basis, right, that goes to RK, but there's also a coordinate map relative to the second basis that also goes to RK, right? So RK. So what, I mean, there's no linear transformation. So, I mean, what is it that connects these things? Well, if we had a vector down here, right, we could get its coordinates by hitting it with the coordinate map like this. To get its coordinates relative to the second basis, we don't want to change it. So this linear transformation should be the linear transformation that doesn't change anything. Well, that's the identity. That's the identity transformation on V, right? So then we can hit the vector little v with the coordinate map for our second basis, right? So what we're really doing here is finding a matrix for the identity transformation, but we're changing the basis, right? So so let's see, how would this work? Well, remember, how we do this calculation is the same as it always has been. We need to express the outputs of the transformation I've called it K. Express the outputs of the transformation as linear combinations of your new basis. Like this. There's some matrix Cij that does this, and that is the matrix that we're looking for. But in this case, what's special about this case is that this linear transformation is actually the identity transformation. So when I write T of V1, that's actually just V1. And up to Vk, which is just T of Vk is just Vk. Okay, so for this special case, where we're just changing the basis, we aren't actually doing a linear transformation, we can find this matrix in exactly the same way, but instead of what this matrix is doing is slightly different. Instead of expressing the images of the v's in terms of the w's, it actually expresses the v's in terms of the w's, so the v's themselves. And that's, because the transformation is really just the identity transformation. So actually calculating this, again, is just solving this linear equation, W1 through WK, times our unknown matrix of coefficients equals V1 through Vk. Now what's different about this special case is that in general, these images might not be a basis for anything. But in this special case, these v's are actually a basis for the same vector space as the w's. So it doesn't actually change the process of doing the calculation, but it does sort of change the result. Okay, so let's look at an example. Let's find the matrix to change from coordinates with respect to this first basis to coordinates with respect to the second basis. All right, well, according to what we just said, right, so these are playing the role of the v's, v1 and v2, and these are playing the role of the w's, w1 and w2. So according to what we just said, we take our w's, we make a matrix out of them, -3, -4, minus 5, minus 7. And then we have our unknown matrix of the C's. It turns out it's going to be 2 by 2, so C11, C12, C21, C22 equals, and then on the right-hand side we put the images of the V's, but because the identity transformation, the transformation here is the identity transformation, the images of the V's are the V's, so 2, 1, 7, 4. Okay, and then we just solve this. So do it however you want. You can augment this left-hand matrix with this right-hand matrix and then row reduce, or you can compute the inverse for this left-hand matrix and then multiply on the left. That's what I did. So the inverse for this matrix, turns out it's minus 7, 5, 4, minus 3. Okay, times minus 3, minus 5, minus 4, minus 7, times my C's equals, so inverse matrix, minus 7, 5, 4, minus 3, times 2, 1, 7, 4. Now these are inverses, at least if I've done the calculation correctly. It looks good because I'm going to get 21 minus 20, so that gives me a 1 in the upper left-hand corner. I'm going to take Sage's word for it, or rather take the word of my ability to transcribe the output from Sage. So right, on the left, this product is just the 2 by 2 identity, so the left-hand side is just Cij, which again is 2 by 2. And on the right, we just need to do this matrix product. So let's see, 2, so minus 14 plus 5 is not minus 9, and then 8 minus 3 is 5, minus, oh boy, minus 49 plus 20 is minus 29, and then let's see, 28 minus 12 is 16. Okay, I hope I did that right. All right, so so what does this matrix actually do? Well, remember what this matrix does is if we have the coordinates for a vector, to produce the coordinates relative to the first basis. To produce the coordinates relative to the second basis, we just multiply by this matrix, right? Since we have found the matrix that takes us from coordinates relative to our first basis to coordinates relative to our second basis. So to check if this actually works, how could we check that this actually works? Well, let's pick a vector where we know the coordinates relative to the first basis. What is such a vector? Well, how about v1? The coordinates for v1 relative to the first basis is 1, 0, right? Since v1 is sort of like a yardstick in the v1 direction, v1 itself is 1 unit in the v1 direction, so its first entry is 1, and it's no units in the v2 direction, so its second entry is 0. So let's take this 1, 0 and multiply it by our matrix of C's. So minus 9, 5, minus 29, 16. We get minus 9, 5. So this here, minus 9, 5, this should be the coordinates of v1 relative to the second basis. Okay, well, how could we check if it really is? Well, remember what the coordinates tell you. What the coordinates tell you is that if you take this coordinate vector, I need to put this on the right. If we take this coordinate vector if we multiply it by the matrix with the w's in it, what we should get is our original vector, v, which was v1. So let's check that this is actually the case, right? So minus 9, 5. The w's are, where are the w's? They're way up here. Minus 3, minus 5, minus 4, minus 7. Okay, so let's work out this matrix product. So let's see, 27 minus 25 is 2, and then 36 minus 35 is 1. So our original vector v1, I hope it's 2, 1. Is it? It is. Okay, it worked. So, right, what we did, so this demonstrates that this vector here really is the coordinates of v1 relative to the second basis, because if we use these coordinates as coefficients on w1 and w2, what we get is, right, that this vector v is actually minus 9 times w1 plus 5 times w2. Right? So all of this is giving us just one demonstration that this matrix is doing its job of turning coordinates relative to the first basis into coordinates relative to the second basis.